And welcome to, I guess it's day 6 of this lecture series. And so I figured, since I've been alluding to non-commutative geometry all along, I should say something about non-commutative geometry. And so the idea is that, we should be able to change, because we got these commutative surface pictures by relaxing the problem. So and moreover, with a Poisson structure, we should be able to get general cases, so actual difference equations via non-commutative geometry. Now, a big question, of course, there is, what is non-commutative geometry? What is a non-commutative surface? So in particular, what is a non-commutative projective surface, or even rational surface? Well, in general, this problem has sort of been approached from several different angles, and it's basically started out with some specific examples of algebras that had the same Hilbert polynomial or the same Hilbert series as a free polynomial algebra, free commutative polynomial algebra. And moreover, at first had some parameter, and if you specialize the parameter, it actually became a commutative polynomial algebra. And so we viewed those graded algebras as non-commutative projective spaces of certain kinds. And people have done, you can do similar things. You can get a non-commutative quadric basically by observing that the main examples of non-commutative P3s turn out to have two central elements of degree 2. And so if you mod out by one of those, you get a non-commutative quadric, i.e. something that's a graded algebra with the same Hilbert series as a quadric in P3. So you can do that and you can get fairly far, but it turns out that there's an approximation you're making there, which is that even if you just think in terms of Poisson structures, if you're deforming a graded algebra and then take the limit as it becomes commutative, that gives you a Poisson structure on the graded algebra. And there's in general going to be an obstruction to expressing a Poisson structure on a projective scheme as a Poisson structure on some homogeneous coordinate ring of that projective scheme. And whether you can write it in that way will in general depend on the line bundle you pick, the ample line bundle you're using to embed it as a graded algebra. So even just in terms of this infinitesimal Poisson structure, it turns out you miss a fair bit if you only look at graded algebras. And in particular, what it turns out is going to happen is that the only cases where you can really write it as a graded algebra is when the ample divisor can be expressed as a linear combination of components of the kernel of the Poisson structure, which is very limited. In particular, in the case of a smooth Poisson structure, the only way you can do that is if you're Del Pezzo, which, there's interesting cases there, but in general, you can't expect that. And so, but the problem is, of course, if you can't even talk about graded algebras, how in the world are you going to talk about your projective scheme, non-commutative scheme? And the other issue is that you can already see in some of these early examples where it is just graded algebras, that even something as simple as what a point means ends up being a more subtle question. And in particular, you find that the actual scheme of points tends to be smaller than you expect. So for instance, in the typical non-commutative P2, the scheme of points is a cubic curve in P2. So you only have a one-dimensional scheme of points in this non-commutative surface. So points don't work very well. Open subsets don't work very well because localization is less fun in the non-commutative setting, because after all, you're not just throwing in reciprocals, you have to throw in reciprocals and allow yourself to left and right multiply by the are the reciprocals, but then you can also multiply by general elements of your ring. And so, it's not even entirely clear what the vector space is of a localization, and that gets tricky. So if we can't even talk about open sets, it's hopeless to try to talk about non-commutative schemes as geometric objects. So instead, what eventually got settled on is really a more modern perspective, which is, rather than try to talk about the scheme itself, we look at the category of sheaves. And of course, this is ideal for our purposes because what we want to understand is not actually the surface itself, but certain sheaves on that surface. So if we can understand the category of sheaves, that's good enough. So the actual definition is, there's something called a quasi-scheme, which is a pair of well, I'm not going to say you all the adjectives, but a reasonably nice abelian category, which I will call cox, although you can also define it, it's actually probably better to define in terms of q cox. So which we call the category of quasi-coherent sheaves on the quasi-scheme, with a chosen object, which we denote by OX and call the structure sheaf. So in other words, we just look at the pair of the quasi-coherent sheaves on a commutative scheme together with the structure sheaf of the commutative scheme, and then that's the thing we're generalizing. Okay, now, since this, of course, includes every scheme, this is a bit too general for our purposes. And one issue is that we don't actually know a good definition of non-commutative projective surfaces, even for surfaces. But what we do know is, we have a sort of vague intuition of, okay, there are things that look like the category of sheaves on a commutative projective surface together with the structure sheaf. And so that's the thing that we want to try to deal with. So in particular, one thing that should qualify is if we have a flat family of categories, of abelian categories, one fiber of which is the category of quasi-coherent sheaves on a commutative surface, we should think of everything in that family as a commutative surface. And so with that in mind, there were several constructions in the literature. So the earliest one, well, it was not actually the earliest non-commutative projective scheme, but it was given the same name as the earliest example of a non-commutative projective scheme, despite that author not actually being involved in this construction. So non-commutative projective planes. So this is incorrectly called a Sklianin algebra. So it's really due to I believe the two collections of authors. So Art and Tate, Vandenberg, and Odesky, which might be joined with Fagan, I'm not sure. So Sklianin actually had originally come up with a non-commutative P3, and so this is a non-commutative P2. So this is basically an algebra with Hilbert series 1/1 minus t cubed coming from a cubic curve in a commutative P2 together with a choice of Q in pick not of that cubic curve. So the generic thing C is an elliptic is, genus smooth genus 1. And so Q is a point on the corresponding elliptic curve. And then in the other cases you get, there's the nodal cases where pick naught is the multiplicative group, and there's cuspidal or non-reduced cases where pick naught is the additive group. So, and then each one of these gives rise to a graded algebra. And then we take, so this is not a quasi-scheme because it's just a graded algebra, but basically Serre's trick for turning a graded algebra into the category, for producing the category of sheaves from a graded algebra works even in the non-commutative case. So the idea is we look at, so given this algebra, let me call this algebra A, so that we take graded A modules modulo torsion A modules, which is basically those A modules that are generated by elements that have that in turn generate finite dimensional modules. So we can't just say finite dimensional modules because that's too small if we're allowing not infinitely generated modules. But basically, so torsion is basically the completion of finite dimensional A modules. So, and of course, this is, if A is a commutative graded algebra, this is exactly the Serre's construction of the category of quasi-coherent sheaves. And then, of course, the other thing we take is we need the structure sheaf, and the structure sheaf is just this graded module. So that's relatively straightforward. Okay. Now, and moreover, because this A is varying over a flat family, and basically the flat family of cubic curves with a marked point in pick naught, this family of categories is a flat family of categories. So that's the first construction. The second construction is there's a construction of P1 bundles over commutative schemes. Due to Vandenberg. And I'll be giving a variant of this construction shortly. And then finally, there's a construction which is not a direct construction anymore, but a constructing new surfaces from old surfaces, which is blowing up points, except for technical reasons, they have to be points in commutative curves in non-commutative surfaces. Well, okay, it also you can also apply it to points in commutative surfaces and you get the usual blow up, but in any case. And as I said, we don't actually have a good definition of non-commutative surfaces. So the way this works is there's a notion of a divisor, and the condition is that the divisor, which is a particular subcategory, has to be the category of quasi-coherent sheaves on a commutative curve. And then once you have that, you can talk about points in that on that commutative curve, and then there's a construction of blowing up. Okay, and this is also Vandenberg. So this is great because it tells us that iterated blowouts of real surfaces and also non-commutative P2, all of that exists. And so we can take those as our non-commutative surfaces. There's only two tiny problems, actually three tiny problems, but the one of them is that this annoying technical condition that you can only blow up points that are in commutative curves, it turns out to actually take a little bit of work to show that it's actually satisfied. So for instance, to show that these P1 bundles actually have a curve of points, which is a divisor, is a non-trivial statement that requires a little bit of proof. And then showing that when you blow up a point here, that you retain a curve worth of points, so you can keep blowing up, again, requires some proof. So the problems are First is show that there's a curve. And let's call it Q of points, which is the divisor. And I should say the reason why I've taken to calling this Q, apart from the fact that C is way too useful to sort of tie up with just one particular curve. So it's nice because I need a name for the spectral curve too, after all. But Q is basically you can think of as a quote scheme. Namely, it's the scheme that parameterizes quotients of the structure sheaf that have Hilbert polynomial, whatever that means, 1. So basically, if you're starting with a graded algebra, it really is, quotients of the graded algebra, which are one-dimensional in every degree. And that's sort of the natural notion of what a point module would be. And so, or actually one-dimensional in sufficiently high degrees, I guess is what we really want. And so that turns out to be classified in all of these cases by a perfectly reasonable projective scheme, which turns out to be a curve and actually turns out to be a divisor. So one can show this. The next problem is more having to do with the original motivation, is that none of these constructions involve difference or differential operators. So we have these non-commutative surfaces, but we also need a way of translating sheaves on those non-commutative surfaces, or at least one-dimensional sheaves, whatever that means, into difference equations or differential equations, and vice versa. And so we need something like that. And the obvious way of doing that would be if we could actually have some sort of representation of this category, or maybe some especially big subcategory where the morphisms are actually difference or differential operators. And we'll see this actually does, that this does pan out. There is, in fact, if you look at the subcategory of line bundles, whatever those are, the morphisms in that category actually do have a representation as difference or differential operators as appropriate, given a choice of ruling. Okay, and then the final problem, which is really the most subtle, the most difficult problem to deal with, is that we don't know, well, we don't understand how these constructions interact. For instance, if you blow up, we mentioned earlier, if you blow up a point on a ruled surface, you can blow down the original fiber, which I mean, the fiber becomes a -1 curve, which you can then blow down, and you get a different ruled surface. Or in other words, a 1-point blow up of a ruled surface is a ruled surface in 2 different ways. This is not something that follows easily from the constructions in the non-commutative setting. And there's some similar issues. For instance, the mere fact that P1 cross P1 has 2 different rulings is a relatively subtle statement in non-commutative land. And in particular, even when you have an interpretation in terms of operators, and you can basically just try to prove that yes, you have this sort of you have something given by generators and relations, and you prove that the relations are invariant, there's still something like 16 different cases. And all of these more complicated things you might do, like commuting of blowups or elementary transformations, pick up even more cases. And in some cases, like for commuting blowups, a priori, there's something like infinitely many cases. And so it's not, you'd have to figure out how to group them into different subcases, subfamilies you can handle separately, and it would just be a horrible mess. So there's definitely an issue there. And so I can finesse this at the cost of using heavier machinery. So let me first talk about 1. So where do operators come from? So, so originally, I mean, the first version of the construction that actually got non-commutative surfaces involved in this integrable system slash special functions setting basically came from an observation. So there's a slight lie above, which is that Sklyanin's algebra, which is a certain non-commutative P3, actually does have a connection to certain, at least in the elliptic case, certain elliptic difference operators. To be precise, Sklyanin's algebra has a representation, or has a family of representations as, well, what if you look at them, turns out to be symmetric elliptic difference operators. Now, the interest, so this algebra is, it's a non-commutative P3. So it has 4 generators and I guess 10 relations, no, 6 relations. Yeah, 4 choose 2. And those relations turn out to basically give you the right Hilbert series in general. But it turns out that there's this, well, actually, so Sklyanin's actually original papers, he had 2 papers. One of them said, here's this algebra. It looks like it's a flat family. And then the other one is, here's the representation of the algebra. And actually, he only really talked about finite dimensional representations, but it's easy to see, because he describes those finite dimensional representations using difference operators, it's easy to see that they actually extend to infinite dimensional representations in meromorphic functions where all the generators are acting as operators. And so you can then just turn it into a formal representation as operators. Okay. And in fact, it's not, but if you look at it carefully, it's not actually a representation of P3, because all of these representations is actually killing a central element of degree 2. So it's really, in fact, a representation of a non-commutative quadric. So this is a good start, because it's actually telling us that, hey, we at least get some example of a non-commutative quadric, i.e. P1 cross P1, that has a representation as difference operators. And in fact, the map from representations to central elements is 2 to 1. So each quadric has 2 representations, which is what we expect. We expect 1 representation per Rille. Okay, so this is the original idea. And so basically then, starting with this idea and later realizing, and then thinking about sort of how one would try to build in blowups. Because after all, if this is basically telling us how to look at generators of, multiples of S plus F, because that's, the quadric embedding in P3 corresponds to the divisor class S plus F. And so this tells us how to take anything in, which is in the line bundle of, ds plus df will give you dth order operators. But in fact, actually, if you look at it a little more carefully, you see that there are, in fact, you can sort of split up some of these elements as a product of a multiplication operator and a difference operator with lower degree coefficients. And so you can actually extend this at the cost of not being a graded algebra anymore. So what this extends to is a representation of, well, basically extends to a category with objects basically the objects are divisors on the actual commutative surface, or divisor classes if you really want to be precise, such that, well, which is generically generated by, it has two types of generators. So it has two elements of degree S, sorry, put the scare quotes in the right place, from each object, and two elements of degree F from each object. Where by the degree, I just mean if you have a these objects are basically points in this lattice, and the degree of a morphism from point A to point B is B minus A. So in other words, we have a grid, and we have two vertical generators and two horizontal generators from every object. And these commute internally and satisfy four relations in each square. Which is just basically saying that the things you can get by going up and then across are equal to the things you can get by going across and then up. And so there's a tricky thing, but it turns out that if you just sort of ask for reasonably obvious consistency relations to hold, that this actually, the relation for each square you can propagate, which incidentally is a completely different kind of integrable system, but it turns out it actually is integrable. That is, if you look at, this relation is some 4x4 matrix, or really 2x2x2x2 tensor, if you really want to be precise. And there's an operator taking tensors like that to tensors that sort of moves you one square to the right and moves you one square up. And if you move any distance in this grid, the degrees of the coefficients only grow quadratically as opposed to exponentially, which is what you expect when you take big compositions. So this is actually a discrete integrable system and one of the other notions of integrability. I don't know about any lax pair, but basically, so the relations propagate. And this turns out actually form a non-commutative analog of a Gurovny basis. And so you can actually use the consistency relations between these relations actually suffice to tell you that the dimension in degree ds plus d prime f is d plus 1 times d prime plus 1. And so you get something flat. Now there's a few caveats because every once in a while, it's not actually generated by these two elements for certain special values of the parameters, which annoyingly are Zariski dense, but issues. But basically, with a little bit of care, you can actually tweak this so that actually you just plain get a flat family. But in any case, so we get this, and then so in particular, you get this P1, this analog of a P1 cross P1 for any elliptic curve together with. It turns out the two parameters are, you basically have 2 degree 2 line bundles and 1 degree 0 line bundle to specify this data. So basically the degree 2 line bundles are, well, the horizontal things are a section of a degree 2 line bundle. The vertical things are a section of a degree 2 line bundle. And then when you move around, you shift your, twist your degree 2 line bundle by this degree 0 line bundle. And so basically this is Q tensor, the original guy, and this is Q tensor, the original guy. And then the relation is that the elements of the degree 4 line bundle you get by multiplying this section with this section are the same as the elements you get by multiplying this way. And so you just basically identify them if they give the elements in the two tensor products, if they're the same element of your line of your degree 4 line bundle. So there's a very simple way of writing down these relations from your data. Okay, so, okay. And then you can you can then ask, okay, what about blowing up? What should that correspond to? Well, blowing up should correspond to, imposing some condition that your section vanished at your point. And okay, if to vanish once, you basically say, okay, well, I just want my leading coefficient in some reasonable sense to vanish at that point. And to vanish with higher multiplicity, well, okay, if you multiply two things that vanish at that point, at the same point where you have to be a little careful about what that means, you expect to get something where it vanishes with multiplicity 2. And so that basically imposes two conditions on the leading coefficient and one condition on the next coefficient down. So you can define that in terms of difference operators as well. And again, it doesn't always work, but there's coherent ways of taking limits. And so you can, using this, you can actually define in this elliptic setting a category that deforms the category of line bundles on a commutative surface. So in the end, we get a category with objects. Well, the objects are basically just pick of our favorite commutative rational surface, which we recall is independent of the surface. I mean, it just basically, we have this basis coming from a blowdown structure. So we get a category with these objects in which every morphism is an operator, and well, in this case, a symmetric elliptic difference operator. Oh yeah, I forgot to say here, the horizontals, or basically the degree f, is multiplication. And the horizontals are certain difference operators. And the swapping the two rulings transposes the diagram, so swaps multiplication and difference operators, which is the original reason why I think of it as a Fourier transform. Okay, so every morphism is just, so we have this category, every morphism is a symmetric difference, elliptic difference operator. And moreover, the dimensions are all constant as our parameters vary. The amusing thing is that it's actually not trivial to do this even for the commutative case, because in general, for commutative surfaces, the number of global sections of a line bundle depends on the surface. But it turns out there's actually a canonical way of picking out only some global sections of those line bundles in such a way you actually get a flat family. And that has this non-commutative deformation. Okay, so this gives you sort of the generic case. Of non-commutative rational surfaces. So you'll note that the way to get around the fact that we don't have good deformations if we only take, if we pick a line bundle first and look at the graded algebra, is to basically say, we're just going to take all line bundles. This also helps get around the question of trying to figure out, what ample bundles, which ample bundle to use to make things work nicely. So we just cheat to use every line bundle. Okay, so this is so far so good. But the problem is that in this generality can't work for more degenerate cases. So it has to fail for degenerate cases because the flatness result is too good. So basically, once you have, for instance, a -3 curve, this ability to pick out a canonical subspace of your space of global section starts to break. And you can prove that basically that there's just no good way of doing that and still get something flat. And still get a vector bundle on your parameter space. So this is going to fail. And so we need something else. So the other ingredient here is that there's actually a multivariate version of this picture, which is somewhat, well, closely related to the theory of Macdonald polynomials. In particular, there's an elliptic version of Macdonald polynomials, which are certain biorthogonal functions that satisfy analogs of the main properties of Macdonald polynomials. And one can construct operators that act nicely on those functions by generalizing this above construction in a particular way. So you basically get a deformation of the symmetric powers of the above family. So this is again elliptic. And again, I don't know how to do this for degenerate cases because again, the flatness result is too strong. But by looking at this construction, it turns out there's a way of, this actually gives you insight into how to construct at least ruled surfaces for more degenerate cases. So the key new notion in the multivariate case is something called a double affine Heck algebra, or an elliptic double affine Heck algebra to be precise. And so, and there's a general construction of these for any root system, well, any reasonably integrable root system, but in particular, these correspond to type Cn. And in particular, rank 1 gives you an actually slightly different construction of these original categories of operators. Although when you sort of trace through what's going on, you realize in the end that they actually are the same operators coming up. So what we're going to do is we're going to generalize the rank 1 case. So, and this leads to the following construction. So let's first forget about the double affine business, and we'll just talk about the simplest possible thing, which is basically the affine Heck algebra, if you will. So what does that look like if you sort of squint at it from a distance? So and we're going to do things locally as much as possible to begin with. So because there's some issues with gluing things together. So we're going to pretend everything can be made affine. So let R be a commutative ring. And in fact, I'm going to assume that it's regular just to make life easier. So basically, R, if you like, is the ring of the ring of functions on some open subset of a smooth projective curve. And let S be a quadratic extension of R. So if you like, S is obtained by adjoining a variable and quotienting by a quadratic equation. Okay. And I'm going to be lazy and pretend that we're not in characteristic 2 and complete the square. Everything I'm saying can be made to work with in characteristic 2 as long as you're careful. But for simplicity, I'm going to complete the square. So basically, all we're doing is we're adjoining the square root of an element of R. Now, it's worth noting B can be 0 here. So we're allowed to talk about the non-reduced case. So in particular, there's no assumption here that S itself is regular. It can be as singular as you like. Okay. So we're then going to define an algebra. So note that S is a free R module. So we get an algebra which is just the endomorphism ring of that R module viewed as an R module. Now, this is not very interesting as an algebra because, of course, it's isomorphic to 2x2 matrices over R, which I think we understand that algebra pretty well. But this algebra has an interpretation in terms of operators. Now, they're not quite difference operators in the usual sense, but they are operators of a kite. So note that endr of S is free as a left S module with basis. Well, okay, one basis element is the operator 1, the identity operator. And the other one is an operator I call n for nilpotent, because, well, it squares to 0, we'll see. And so n takes, let me call this alpha, just so I can use A and B later. So it takes n, so n of A plus by is B. Okay. And where, of course, we're viewing B as an element of R, which is a subring of S. So we're viewing it as an element of S. Okay. And this is pretty straightforward because, in fact, as a R module, it has basis n, yn, and y, and y, which are just basically the operators that spit out B, that spit out A, that spit out by, and spit out ay. So in other words, the 4 matrix coefficient, the 4 entries in our 2x2 matrix. And S has basis 1y. Sorry, and then and yn plus ny is equal to 1. So basically, we can take this basis n and ny and turn the ny into a 1. Okay. It's also true that it's free as a right arm S module with basis, with the same basis. But the two, the viewing it as left basis and viewing it as right basis are not actually compatible. So in general, as a bi module, This is only a filtration. But a very useful filtration for actually proving things later. Okay, so this is a very simple algebra, but the point is N has this description. So on the one hand, it's taking A plus BY to B, which is very straightforward, but we can also write this as taking F, an element of S, to F minus F bar over 2y, where F bar, where bar is the involution corresponding to this quadratic extension. Okay, and if you think of it this way, this starts to look more like a difference operator because, F bar morally is the same as F of minus Z, if you like, or F of 1 over Z. It's applying, if you think of F as a function on something, namely spec of S, F bar is applying this involution to the argument of the function. And so we're taking this, so we get this operator which involves this particular reflection on S. And we take linear combinations of that and the identity, and that gives us this operator N. So anything in this algebra has this description as a linear combination of F and F bar, where we allowed some mild pulls. Note, this only works as stated when y is a cancelable, or is a non-zero divisor. Because we need to be able to divide by 1 for this to actually make sense, but that's okay. We'll see later that in the case where the remaining case where we can't divide by y is basically because y squared equals 0, and we'll see in those cases you can again write, well, not so much n itself, but the thing we are actually eventually going to care about as an operator as well. So this won't be a problem. Okay, so far so good, but this is not all that, you can't do much with this. So you get an interesting algebra. We're going to assume that this algebra S is a quadratic extension in 2 different ways. So in other words, we have 2 algebras, R1 and R2, contain an S, and S is free of rank 2 over either one of them. And in particular, so we have S is R1 plus Y1 R1 and R2 plus Y2 R2, where yi squared is in Ri. So this is this thing which is double covered in 2 different ways. And of course, geometrically, this seems a little weird algebraically, but geometrically, this is perfectly reasonable. We're just saying that we have this scheme, in this case, this affine scheme, but we have this scheme which has 2 involutions acting on it. And then R1 and R2 are just the quotients by those 2 involutions. So from that perspective, this is perfectly reasonable. Okay. And right. And so then we get 2 different algebras. So we get the algebra and R1 of S, and we get the algebra and R2 of S. And what we're going to do is, roughly speaking, take the algebra generated by both of them. So in other words, we're allowed to either do R1 linear things or R2 linear things, and then we can compose them in arbitrary ways. Now, this is not quite the right thing for our purposes, because this is essentially affine. I mean, if you sort of trace through what's going on and, figure out what the relations ought to be, and then take the limit where R1 and R2 end up being the same after all, what you find is that this ends up being basically 2x2 matrices over an affine, so just a regular polynomial ring over S. I think it says. So it's not quite the right, it's not compact enough for our purposes. So instead, what we're going to do is we're going to define a category where the objects are Z, so one object for each integer, such that going from I, well, so firstly, the endomorphism module of I, of the ith object, is either and R1 of S or and R2, depending on parity. And we have a morphism from I to I plus 1 that acts as 1. Okay. And what we see in general is that basically by generalizing that filtration in terms of 1 and n, we find that Hom from I to j is a free left S module, or as an S bimodule has a filtration, natural filtration of rank 2j minus I plus 1, or 0 if j is less than I. Or in other words, except for the fact that we basically, well, I mean, as an R module, we get it's now 4. And so except for the fact that we multiply all the dimensions by 4, these are what you expect for basically the category where the maps from I to j are homogeneous polynomials in 2 variables of degree j minus I. Or if you like, it's the same Hilbert series as 2x2 matrices over homogeneous polynomials. Okay. And that second perspective tells us how to make it look more like homogeneous polynomials. So actually, it turns out already starting from this, you can already use this to actually directly construct the category we care about, the ruled surface category we care about. But there's a way of doing it that makes it clearer that it's a flat deformation of something commutative. So to get the actual correct category, we basically take a subquotient. So on the one hand, we identify elements if they have the same image on elements of Ri, where it's the, I mean, Ri basically where I just mean I mod 2. And B, we insist that the image of such an element is in Rj. So if you like, is taking symmetric things to symmetric things. Or I mean, so we don't care about what it does to to non-symmetric things, and it takes symmetric things to symmetric things. And because the image is in RJ, the composition still makes sense on this subquotient. And generically, this is a Morito equivalence. In other words, it gives us the same category of representations. Okay. And so the category, so the P1 bundle is the quotient of modules over this category, i.e. functors to modules over your base ring, or base field if you prefer, by bounded above modules. So basically, it's the same idea of graded modules mod torsion, except we're no longer quite a graded thing, but we sort of retain enough structure like that. Okay, so that's how we get our non-commutative category. Okay, where does the representations come from? I mean, where do the operators come from? So the point is, operators from Ri to Ri plus 1, which are what's generating this. Well, what are they doing? They're taking an element of Ri, viewing it as an element of S, and then applying an Ri plus 1 linear thing to that, and then requiring the result to be an element of Ri plus 1. So they look like Ni plus 1 times F. So we multiply by some element of S and then take the coefficient of I plus 1. So what do these look like in general? Well, so there's basically two cases. Modulo is really annoying, weird characteristic 2 case that, anyway. So there's two main cases. The first is that y squared or yi squared are non-zero, and because so we're assuming we're a domain, so this is, or at least actually we're not quite assuming we're a domain, but we're assuming R is a domain, so we're in good shape. So if we're taking square roots of non-zero elements, then bar, I mean, this description in terms of take f minus f bar and divide by yi plus 1 makes sense. So ni plus 1 f applied to Ri, where Ri is in capital Ri, is Fri minus, let's say, iota I plus 1 Fri, where iota I plus 1 is the involution. Okay. But Ri is invariant under the other involution. So we can, well, of course, the involution is a homomorphism, so we can factor that. And then we can say that Ri is equal to iota I Ri. So this is iota I plus 1 iota I applied to Ri. Now, the reason the significance of this is that in the nice cases, I mean, so if you look at sort of one of the typical cases is, modulo things being affine, S is an elliptic curve, and the two involutions are both hyperelliptic. So they're basically, negation up to a translation. But if you take two of those and compose them, you get a translation. And so this actually looks like a difference operator. So we get a difference operator where the shift is iota I plus 1 iota I. And inductively, you see that anything in this subquotient category has such a representation as a difference operator, where the shifts are powers of the composition of your two involutions. The other case is that you're non-reduced. And then you have to think a little bit about how the rings embed. So on the one hand, S is R1 bracket Y1 mod Y1 squared. And it's easy to see that R2 has to be isomorphic to R1. But the way that R2 embeds is actually going to look like R maps to R plus, well, dr over omega y1, where dr is some derivation, basically, or rather dr over omega is a derivation. Or in other words, the coefficient of y1 after we embedded is basically the derivative of r. And so going from R1 to R2 looks like a differential operator. So in either case, we get an operator of the kind we want. And in this first case where we're getting difference operators, we can further refine this, depending on whether S is integral or whether it's two copies of R. And basically, so that gives us the symmetric case and the non-symmetric case, and so forth. So the upshot is, so this P1 bundle has a representation as difference or differential operators. And therefore, in particular, any module is automatically going to induce an equation. It may not be holonomic if the module has the wrong dimension or something, but it'll automatically induce an equation. Because basically, the other way of saying it is because we have this representation as difference or differential operators, that basically means that meromorphic functions are a module. And so given any reasonably finite module, we take maps from that to the meromorphic functions, and the maps like that are basically the solutions of some equation. Okay, and then so some more work. We need to actually globalize things. Gives a P1 bundle over a non-affine picture, i.e. we have a non-affine scheme S, which is a double cover in two different ways, which is represented by twisted difference or differential operators. Which, in other words, locally in a suitable sense. So remember we mentioned earlier that once you have these automorphisms acting, these translations acting, you don't necessarily have invariant open subsets, but you do in general have invariant intersections of open subsets, and you can still cover your thing by such invariant intersections. And so on each one of those invariant intersections of open subsets, you get an affine picture, and thus an affine Z category with objects integers. This is called a Z algebra in the literature. So you get this P1 bundle over your affine picture, and then you just need to basically, given two such affine things, take an isomorphism between the algebras on the intersection to glue it together. And that basically gives you something which is very much a twisted sort of operator. Okay, and so in the end, what we get is, so for S, well, for curves, this reconstructs Vandenberg's original construction of P1 bundles. There's some technical reasons why it doesn't quite capture everything in Vandenberg's construction over higher dimensional things, but over regular curves, it's perfectly fine. Okay, and so by reconstructing it, we've shown that Vandenberg's construction, Vandenberg's notion of real surfaces have these representations as operators, and therefore sheaves on those things correspond to equations, and vice versa equations, we can represent our equations in terms of these operators and go back and recover sheaves. Okay, so far so good. So this explains this dictionary between equations and sheaves in this more non-commutative picture. But we're then stuck with this issue of how do we show consistency of, as I said, even P1 cross P1 having multiple rulings basically requires you to write down, if you try to do it this way, you're basically forced to write down all 16 different Fourier transforms, which, okay, you can do, but, and I've done it, but it's still a lot of work and not very conceptual. So how do we explain things more generally? So it turns out that there's a third, well, construction isn't quite right. Or rather it is, but it's misleading of these abelian categories. And the way this works is actually going back to something we used in our translation between equations and sheaves originally, which is that, so on P1, we observed that every sheaf on P1 fits into the middle of this 5-term exact sequence where the other terms are powers of O of -1 and powers of the structure sheaf. And slightly more sophisticated way of saying this is that every object in the derived category of P1 is the cone of a morphism from a complex where every term is a power of O of -1, mapping to a complex where every term is a power of the structure sheaf. And moreover, this relativizes, and so works for ruled surfaces. And it turns out that this actually works for non-commutative ruled surfaces as well. So the derived category, so if X is one of these P1 bundles, where the where the two curves, the two bases of the two quadratic extensions are C1 and C2, then any object in the derived category of quasi-coherent sheaves on X fits into a distinguished triangle. In fact, a functorial distinguished triangle. Where we have not quite over -1, but basically the pullback twisted by -1, or by the relative -1. It's worth noting that, unlike in the commutative case, this doesn't actually decompose as the product of pullback and twisting. It's really a twisted pullback that you can only do in sort of one step. That's okay. Going to row up. Well, let me in fact say this is, say, row 1 and 1 star to row 2 star and 2 star goes to your sheaf and then cycles around. Where M1 is a quasi-coherent complex on C1, and M2 is a quasi-coherent complex on C2. Okay. So to specify a sheaf on X, and in fact, this is not just a functorial distinguished triangle, it's a unique functorial distinguished triangle. So to specify a sheaf on an object on X, a complex on X, we need to specify a complex on C1, a complex on C2, and this map. Well, what is this map? Well, the maps are basically mediated by the maps pi, where pi, we write it as q bar, but basically pi 1 and pi 2 are our double covering maps. I'm writing it as q bar because it turns out it's not actually quite the same as the actual curve of points that we get in general. So in fact, I might even be wrong. It might even be, I think it's actually q hat in the paper. Hat for horizontal. Basically, it only tells you about the horizontal components of the curve of points inside this ruled surface. Okay, so the upshot is that we get a description of objects in our category in terms of an object on C1, an object on C2, and a map on the common double cover. So just the input data. Oh, and sorry, there's also a line bundle in the picture because these are twisted operators. So there's a line bundle. But so far, so good. And if you look at this, you see that this is essentially the same data that shows up in going from Higgs bundles to sheaves, where the only difference is that in the Higgs relaxation, pi 1 and pi 2 are the same. So this is what we get, and this really does directly correspond to a matrix form equation. If if M1 and M2 are both sheaves, or both vector bundles of the same rank, this exactly looks like a matrix form equation, modulus a little twisting information. And moreover, in the non-reduced case, where pi1 and pi2 are the same, you're looking at the double diagonal in C1 cross C2, which is where C1 and C2 are the same. And you have this map on the double diagonal. Well, that's essentially what a connection looks like algebraically is a map on the double diagonal that's one on the diagonal. But we can instead get that by a map between, we can always sort of, a meromorphic thing like that can be factored as a holomorphic thing, mapping from pullback to pullback on the double diagonal, and then we divide by the image on the diagonal itself to get a meromorphic connection. So this really does sort of, this description here really encapsulates exactly what we want to have showing up for equations. So this is, if you like, this data like this, you can think of as a derived analog of an equation. So instead of basically being a connection on a vector bundle, it's a connection on a complex. But it's exactly what we want. Okay. And then this description can be used to construct the derived category. So rather than having to define this abelian category, look at complexes, you look at injective complexes on that thing, and then do the usual quotienting and modding up by homotopy category, all the various things, quotienting by quasi-isomorphisms, all that nasty stuff. We can basically sidestep and just go directly to, we understand the derived category of C1, we understand the derived category of C2, because those are nice commutative things. I mean, they're smooth curve. It doesn't get that much nicer than the derived category of a smooth curve. And this extra data of how to glue them together, and you can actually reconstruct the derived category in this from that data. Okay. Now the problem, of course, is if I just hand you a derived category, or if I just hand you a triangulated category, it doesn't tell you anything about any additive category that it might have been the derived category of. But there's also, we can also characterize the objects that are non-negative. That is, that only have cohomology in non-negative degree. And then similarly, once you characterize that, you also characterize the things that are non-positive because there's a certain orthogonality there. So this is called the T structure. And if you know which objects are non-negative, and as if that tells you which things are non-positive, a sheaf is something which is both non-negative and non-positive, as you know what the sheaves are. And that actually, so with that characterization, you actually recover the original abelian category. And the rough idea here is that there's a duality. So there's a version of Serre duality. Which is basically, there's this functor on the derived category, capital S, that gives rise to duality. And if we define theta to be a certain shift of this Serre functor, then theta is actually an abelian functor. So it's in particular it's exact. So in the commutative case, it's twisting by the canonical sheaf, by the canonical bundle. So we expect it to be exact. And in particular, our complex M is non-negative if and only if the direct image onto C1 of any power of theta applied to M is non-negative. Which, roughly speaking, is saying that our ruled surface is relatively Fano. Which, again, geometrically is what we expect. The anticanonical bundle is relatively ample for a ruled surface. Okay. And it turns out, now, there's some big caveats here. The biggest caveat is that the only way I can actually prove these statements about the derived category is by using this construction, this earlier construction of the abelian category. So I can't actually use this to sort of start for ab initio to just construct the derived category, construct the T structure to define the abelian category and say anything useful about it. I can't even directly prove that that this category we get is the derived, that we actually are the derived category, this abelian category we're constructing. But once you know that, it gives you an alternate characterization of this category, of this non-commutative ruled surface, which turns out to be very useful. And so there are similar things for non-commutative P2 and for blowups. And we can define the abelian equivalences we want. Things like being able to swap blowups in distinct points by writing down the derived equivalences and showing their, let's say, left exact. Because we know what it means to be non-negative, so we know what it means to be left exact, namely it takes non-negative complexes to non-negative complexes. And if a derived equivalence is left exact and its inverse is left exact, then the derived equivalence actually preserves sheaves. And so gives you an abelian equivalence. And this is the only way I've figured out the only way I've been able to prove these things without getting into this whole combinatorial explosion business. Okay, so now, so this gives you some things for free. Like the duality is basically inherited from Serre duality on C1 and C2. And everything is nice and intrinsic, so that's all good. Some other things get a little trickier. But right, so let me, what was I going to say? Right, so, but basically once you have this theory and once you've shown that, especially once you've shown that these autoequivalents, that these abelian equivalences really are abelian equivalences, huge amounts of the theory that we've already developed in the commutative case just carries over directly. So this description of the derived category tells you what the Grothendieck group of this abelian category is, because the Grothendieck group of an abelian category is the same as the Grothendieck group of its derived category. And if you have this kind of, it's called a semi-orthogonal decomposition, the Grothendieck group of the glued category is just the sum of the two Grothendieck groups. And so you understand a huge amount about these categories just by the way that these derived categories were constructed. And so that actually lets you show, for instance, that this Coxeter group theory, this idea of the fundamental chamber still works. And you can characterize ample bundles. Well, and one thing you get from the Gorodny group is you actually get a notion of dimension of a sheaf. Because on a commutative surface, you can read off the rank. The rank is a functional on the Gorodny group. But the Gorodny group is independent of our non-commutative parameter. And so you can still read off the rank even in these non-commutative cases. And so a one-dimensional sheaf is a sheaf where the rank is 0. Similarly, a zero-dimensional sheaf, well, there's this pairing on the Gorodny group coming from this, when you take the X groups and you take the alternating sum of dimensions of X groups, the usual sort of Euler characteristic thing. We alluded to this earlier. And the dual to the one-dimensional things turns out to be the zero-dimensional things. So basically the things that have trivial pairing with every one-dimensional thing, those are precisely the zero-dimensional classes. The analog of the Picard lattice is the quotient of one-dimensional things by zero-dimensional things. And that's basically how you would define divisor classes on your non-commutative surface. So you can basically build up all of these ideas that we've been using before using this non-commutative setting. Some other things we can say is, so the moduli stack of non-commutative surfaces, well, let me say rational surfaces because the answer is nicest there, actually has a natural fibration over the stack of anticanonical commutative surfaces. Here, as a technical issue, when we talk about a non-commutative rational surface that happens to be commutative, we're assuming an anticanonical curve as part of the structure. So it's fibered over the stack of anticanonical commutative surfaces, and the fibers is exactly the identity component of the Picard group of the anticanonical curve. So in other words, given a commutative surface with an anticanonical curve and a line bundle which is degree 0 in every component of the anticanonical curve, there's a corresponding non-commutative surface. And you'll notice that this parameter, you can read, when you're coming from an equation, you can read off the parameter or the type of the parameter basically from the type of equation. If it's an elliptic difference equation, the parameter is a point on the elliptic curve. If it's a Q difference equation, the parameter is Q. If it's an ordinary difference equation, the parameter is a point in the additive group, which is basically, we usually rescale it to 1, but it's basically the thing you're translating by. So H bar if you want to actually give it a name. And in the differential case, the parameter is also in the additive group, which again basically is an H bar-y thing and this comes from the fact that we can always Fourier transform the differential case to the additive case. So we need this additive parameter, excuse me, surviving in the picture. So we have this extra parameter. Now, there's a very nice description of what's going on here in terms of the derived category. So if X is a commutative surface, so smooth, projective, rational, anticanonical surface, well, then the structure sheaf is what's called an exceptional object. Which basically says that the X group, the X algebra of OX, so the X from OX to itself, is just basically your base field. That is, it has no non-trivial endomorphisms, and it has no higher endomorphisms, no derived endomorphisms. And what this means is that we actually get a different, we again get this a semi-orthogonal composition. We get a canonical distinguished triangle where so given M in d of x, if we take the kernel of the sort of natural map of global sections, N, so this is functorial, and N has no derived global sections. So in other words, the category of, and let's be really easy here and say that this is coherent, bounded complex with coherent cohomology. So that splits up as basically multiples of the structure sheaf and things that have no derived global sections. And so, but moreover, the map, so if R gamma of N is 0, then Hom from N to the structure sheaf is, well, derived Hom can be identified with derived Hom on our curve Q from the restriction of N to Q to the structure sheaf of Q. And this is because Q is anti-canonical. That is, we have a distinguished triangle where we have this exact functor coming from duality, and the third term is the restriction to Q. In fact, actually for sheaves, this is, I mean, for nice sheaves, this is a short exact sequence. Okay. And so this is just something on the commutative surface. So to make this non-commutative, we simply replace this copy of the structure sheaf by a line bundle in pick not. And then use that to glue together the derived category. And this turns out to give you the correct derived category. You can prove this inductively. Now, okay, so this basically gives you a way of actually turning a commutative surface into a non-commutative surface. There's one very nice special case. So if X is a Sakai surface, that is, let's say k squared equals 0, then we get a non-commutative surface which roughly corresponds to Pain-Levé, or some version of Pain-Levé. And this non-commutative surface is a 2-parameter deformation, or this family of non-commutative surfaces is a 2-parameter deformation of a rational elliptic surface. And if bigger, you can take X. X is the blow up of a del Pezzo surface in some point of the chosen anticanonical bundle. And moreover, it's on the identity component. So our non-commutative deformation, if you start with this del Pezzo surface, we have one parameter, which is the point on the identity component we're blowing up. And we have another parameter, which is a line bundle at degree 0. But this anticanonical curve is a fiber of an elliptic surface. So that's the same type of information as a point on the identity component. So we get 2 points on the identity component describing our non-commutative surface in terms of this del Pezzo surface of degree 1. And we have the following theorem, which basically just involves this description of the derived category. Doesn't use anything about the actual abelian categories in the picture. So the theorem is that there is so relative to the natural action. So let me call this non-commutative surface X plus. So if X plus and X plus prime are in the same orbit, under the action of SL2Z on the 2 parameters, then they are derived equivalent. And as essentially a corollary, if one of them is commutative, then it's a moduli space of sheaves, of one-dimensional sheaves. Sorry, and most one-dimensional sheaves on the other. In other words, we get this 2-parameter family, or actually, I mean, 2-parameter over the del Pezzo surfaces. So we get this family of non-commutative Sakai type surfaces with an action of SL2Z. If we start with any Sakai surface, any commutative Sakai surface, anything in the SL2Z orbit gives you an interpretation of that Sakai surface as a moduli space of at most one-dimensional sheaves. And so in particular, we get one such interpretation for each beta in Q union infinity. Because we're acting by SL2Z, so this is one of the natural homogeneous spaces for SL2Z. And for each such interpretation, each of these gives a different lax pair, or different kind of lax pair for each ruling. And so in particular, so basically if beta is P over Q, we get a, which I've already mentioned before, we get a rank 2Q lax pair where the vector bundle has degree P. And if beta equals infinity, well, we get 0-dimensional sheaves. So not actually a lax pair. But what we see is that for beta, a finite rational number, this gives us an interpretation of the appropriate discrete or continuous Pan-Le equation as an isomonotony deformation of the appropriate Lax pair. And if beta equals infinity, we get an interpretation as changing coordinates on P2 coming from the action of the appropriate Coxeter group on blowdown structures, which is exactly Sakai's description of the Pan-Le hierarchy. So the beta equals infinity case is exactly Sakai's description. And in particular explains why we're still getting the same picture, even though we're using surfaces in a completely different way. And that's because there's this one weird edge case where we have these extra, not quite equivalences, we have these extra derived equivalences between our different, between our different surfaces. So this is one thing. And this is a special case of a, or sorry, I should put order of operations correct. This is a generalization of a non-trivial special case of geometric Langlands. Which morally implies that there exists a discrete geometric Langlands. So geometric Langlands is basically telling you about certain derived equivalences between moduli spaces of connections on vector bundles and non-commutative deformations of moduli spaces of Higgs bundles, basically. And in the special case where they're surfaces and you're over P1 with 4 singular points, this is a special case of this Sakai surface derived equivalence. But this derived equivalence here for surfaces extends to all these different types of discrete equations. And so, it's hard to make this precise as a conjecture, but the rough idea is that we expect that for any one of these non-commutative surfaces, these moduli spaces corresponding to that are classifying equations should themselves have non-commutative deformations. And one piece of evidence for this is that they have Poisson structures. So they morally should be coming from non-commutative deformations. And furthermore, that there should be an action of something like SL2Z on those non-commutative deformations. That should, in particular, induce derived equivalences between those deformed moduli spaces. And then in particular special cases, when everything becomes differential, this should recover the sort of basic derived equivalences in geometric Langlands, at least for GLN. Okay, so this is sort of the big open problem in this area, although it has almost nothing whatsoever to do with integral systems or special functions. But it's an indication that there's a lot else going on in this picture. Some other things I want to mention very briefly. One advantage you get of talking about these things in terms of sheaves is that you do have sheaves which are not one-dimensional, and you can sometimes use those to get useful information about your sheaf. So for instance, straight line forms for equations basically come by taking kernels of surjections from the structure sheaf to the one-dimensional sheaf corresponding to your equation, which in non-commutative land is surjective way more often than you would expect from commutative intuition. And so, basically taking the kernel there and then finding a line bundle that maps into there. Well, maps between line bundles are operators. And so if you have a line bundle mapping to this kernel, mapping to the structure sheaf, mapping to M, this composition is an operator and gives you a straight line form of the equation. So for instance, you can use this to see that in the Garnier cases, although this is already familiar in the differential case, but for the Garnier cases, if you want a straight line form, you need to add in some apparent singularities. And those are exactly encapsulated by basically the divisor class of this sheaf L that has to map in. And basically telling you exactly how many apparent singularities you need to add in order to make this work. And so basically the co-kernel of this map is exactly sort of where the apparent singularities are. So straight line forms can be built into this theory. As I said earlier, the continuous deformations can be understood using this theory, although it's definitely more subtle. The classification of singularities can be made to work. Again, it's quite a bit more subtle because I used things about you have the spectral curve, you can break it up into branches, none of which actually works as described in the non-commutative case, but you can basically finesse things by using the fact that there's this big piece of the derived category, and that's this big piece of the whole picture, which looks exactly the same as in the commutative setting. And so you can take this local information, argue that it extends to something global, which is in this common open subspace of your moduli space. And therefore, you can use what you know from the commutative case to give you information about the non-commutative case. I should also mention that there's some arguments here in the general theory where I actually need to use finite characteristic to prove things. So the biggest thing there is, one of the questions that arises is, given a Chern class, is there an irreducible equation of that Chern class? So in other words, is there an irreducible sheaf of that Chern class, or an irreducible equation with that singularity data? And of course, there's a very important thing to want to know. And I can characterize that, but the characterization basically involves reducing to certain finite characteristic cases where you can turn the problem into a much more commutative problem, and then basically take limits to show, and then show that you can lift that to characteristic 0, and the lift of an irreducible thing ends up still being irreducible, and so you can basically get things that way. But I don't actually know of ways of doing that without going to finite characteristic. So despite the fact that differential equations in finite characteristic are really, really weird, that in the differential case, you have to go to finite characteristic to really settle the question of when those equations are irreducible. And then for other cases, sometimes you don't have to go all the way to finite characteristic, but you're always going to these weird degenerate cases where it's not actually an equation as such. But anyway, so I should probably stop somewhere around here. So let me stop here to leave a little bit of time for questions. But this is, I think, a reasonable place to end things for the lecture series. I realize this is all a lot more abstract than the entire rest of the lecture series. So hopefully what you got was more the flavor of what's going on than actually trying to follow all of the grotty details. And not that I gave all that much in terms of grotty details, but as I said earlier, the important thing to know is that this works. And thus all of the commutative theory I told you before is actually justified.
I have a reference question. So
okay. Oh, right. So the reference for this is, I forget the archive number, but it's non-commutative. Sorry, it's the birational geometry of non-commutative surfaces. Basically, because the paper really takes more of the perspective of proving things about non-commutative surfaces, and then mentions towards the end the application to special functions. So there's an earlier paper, which I think is the birational geometry of elliptic difference equations, but I'm not completely sure, which does the elliptic construction in great detail with sort of telling you explicitly what these operators look like and doing all the proofs. And there's actually a few places where this paper about general surfaces proves that it sort of cites back to that paper because it's exactly the same proof. You just, file off the serial numbers. Yeah, so this is 1907.11301.
Yes.
according to Akane. Thank you. So yeah. So yeah, and if you look through all of these papers, there's a lot of places where there's like, yeah, it's not clear how to prove this more general thing, like showing that you get projective moduli spaces actually is fine for one-dimensional sheaves on non-commutative surfaces. I don't know how to do it for higher rank sheaves, despite the fact that sort of all of the original literature on moduli spaces of sheaves was about basically vector bundles or torsion-free sheaves on, compactifying to torsion-free sheaves. And that's like the one case I can't deal with on these non-commutative surfaces because certain inequalities I just don't know how to prove. It's really frustrating when you're trying to plagiarize proofs from the literature on these things, because they keep doing things like saying, okay, well, we'll take our projective scheme and embed it in PN and then slice it with the hyperplane section. Well, you sort of fail immediately as soon as you try to embed a non-commutative thing in PN. And you just can't do that. So it was quite weird figuring out how to talk about a hyperplane section in PN without doing that enough to work for these one-dimensional cases. But that was sort of good enough because then you can sort of get down to zero-dimensional, and zero-dimensional is a lot easier to deal with. But so there's a lot of places where it's like it's not clear how to prove things, or things that ought to be generalized, or well, like this thing about showing that this description of the abelian category is actually correct without using all of these references, which are themselves pretty long. It would be nice if we could do that, to sort of just be able to do everything from start from this very simple description of the derived category. But also, in any case, there's the other references are all sort of cited from this paper. So like if you want to know more about the Dahas, that paper is cited in here. I think the paper is something like elliptic double affine Hecke algebras is the title for that. So I mean, my titles are usually not all that obscure.
I see.
But
it's okay, but yeah, this paper is already too much.
This is the main one, yeah.
Okay.
Yeah.
So,
but I mean, I don't know sort of who might have insights coming from integral systems or special functions to solve some of these questions. So, yeah. Sorry, Lainey, do you have a question?
Yeah, I have a very naive question.
Okay.
I was thinking back over the whole framework, and my understanding, at least at the beginning, was that you moved to the non-commutative framework because this is the natural setting of the linear problems, the lax pairs, which come with potentially non-commutative matrices. But on the other hand, there are objects that people are calling non-commutative Pain-Levé equations in the literature.
Okay.
These are matrix versions of Pain-Levé equations. Sometimes they are perhaps reinterpretations of hierarchies. I'm not entirely clear on the whole scenario myself.
Okay.
But is it possible that in your framework, in addition to the Sakai scheme, you can also deduce some objects that you might call non-commutative Pain-Levé equations?
Well, I guess in principle, you can say something like that, because you could sort of take Sakai's description and say, okay, well, every non-commutative surface with k² equals 0 and like no -3 curves or worse is an iterated blow up of non-commutative P2. And so you can sort of get these different birational maps between non-commutative P2s, although how you write those down, because this is way more abstract than just, I mean, it's not, I think it's probably true that these birational maps between non-commutative P2s are in fact maps between the fields of fractions, but it's not a priori obvious from the constructions.
Yeah.
So, but in principle, you could get that and you get an elliptic thing like that. I don't know what you would do with that, but you certainly could expect something non-commutative along those lines, which would look very much more like Sakai's thing. I mean, having seen how you write down the elliptic Pain-Levé equation in terms of that description for Sakai, I'm not going to try to do that in a non-commutative setting.
Yeah.
It's long enough as it is. But
Yeah. Okay.
yeah.
Good. Thank you very much for your lectures.
No, you're welcome. Yeah, but yeah, no. As far as these other non-commutative Pendelman equations, I don't know sort of where they might come from. I mean, this is all sort of very dedicated to linear equations, and you sort of only get the nonlinear equations sort of at the end using this by twisting by-line bundles.
Right.
Yeah. All right. I guess the thing I forgot to mention is that there's a notion of twisting by-line bundles here, and it changes the non-commutative surface, and that's why you get non-autonomous equations. Well, in some sense, the stuff on the archive already is a book. It's certainly long enough. My original intention when this is going to be in person is I'd ask a few people, if they had any thoughts about where it would be a good place to publish this, because it certainly seems like this is the right audience for the book. But so if anybody has any thoughts on that, please let me know offline. It would be good to get these published just so that they've actually been peer reviewed and people have found all the holes. But it's not that easy the elliptic paper is like 200 some pages. It's not easy to get those refereed. And even the non-commutative paper is long for most journals. Okay, well, I hope everybody got something out of this. And of course, you can always go back to the stuff on YouTube, or you can look at my slides or what have you, and ask me random questions over email, and see what happens. But